So welcome to lecture 29, or at least it's pre-recording. This lecture is titled Solving Equations. Now it is following a sequence of 3 lectures on plotting. So we continue a little bit the geometric aspect of this course with the Apollonius problem. So the Apollonius problem is a geometric problem, and I will use this problem to motivate the formulation of a system of polynomial equations. The tool in symbolic computation to solve a system of polynomial equations is a Groupner basis, and we spent quite some time defining what is a lexicographical term order. Well, the benefit of this lexicographical term order is that it leads to a triangular form of a polynomial system. Okay, so let's look at the problem of Apollonius. So we have given 3 circles. Here is our example. We have the unit circle centered at 0 with radius 1. Then we have the second circle at center to 0 with radius a little bit small, 2/3. And then the smallest circle is at centered at 1, 1. So we will see in the Jupyter notebook with SageMath that if you provide one circle, then finding another circle that touches the circle reduces 1 degree of freedom. So you can choose the center of the touching circle, and then you can compute the 2 solutions that touch the 2 circles that touch the given circle. So for one circle you have 2 degrees of freedom, so you can impose 2 more circles. Now we will see that there are 8 solutions to this problem. So all solutions are plotted on this slide. All the solutions occur in pairs, and they are plotted, so a pair of 2 solution circles is plotted in the same color. So this picture is probably rather confusing. Therefore I have split it out. So this is a graphics array. So the first plot with the 2 red touching circles is a solution of a polynomial system of 3 quadratic equations, where we have the 3 circles that are given by the centers and the radii. So the equation, so the system of equation has a center x and y, so not x, y, z. So there are 3 variables and we have 3 equations. So typically this leads to only isolated solutions. So you can see that the system here, we have two red solutions, 2 green solutions, 2 black solutions, and then 2 orange solutions. So we will solve this problem systematically with SageMath. Okay, so in SageMath one can typically just type in solve, but it's good to know algebraically what is going on. So we have seen that the term orders of polynomials define a normal form. So with the lexicographical order, so here we have the variables x, y, and r, then all the terms that have x in them, they come first, no matter their degree. So within the terms that have this one x in them, we first put that term in the highest degree in x. Very similar to the dictionary order. Now, what one does when one computes a Groebner basis, one eliminates the leading monomials, and a lexicographical order will ensure that the variable that comes first, so all the terms with that variable, will actually be eliminated. So this leads to a triangular system. So a Groebner basis generalizes the greatest common divisor when one looks at polynomials in one variable, and it also generalizes the row reduction to bring a linear system into triangular form. So for the two red touching circles, that there are two solutions can be seen from the Groebner basis. So if one sets up a lexicographical Groebner basis, then this is the result. You see that there are three equations, and they are a lot simpler than the given equation. So here you see the specific inputs again. So we have the last equation that occurs only in R. And if we have the two values, so this is a degree 2 equation, if we have the two values in R, then, or we can actually leave R for what it is, we can actually see that the center of the touching circle, the coordinates x and y of the center, are explicit formulas in function of the radius. And this shows indeed that you have two solutions for one setup for this problem. So solving polynomial systems is a very complicated problem. In this lecture, we focus on one simple example. The example is simple enough that it can be solved instantaneously, but it's still interesting enough in the sense that it goes beyond the quadratic equation. Although you can see that with a Groebner basis, the problems are reduced or reformulated into quadratic equations. Okay, so these are the slides. So let me, in the second part of this recording, move to the Jupyter notebook. So there will be three parts. What I will try to illustrate, explain in the first part, is how one can derive the equations. And to make this somehow interesting, I will make a new Jupyter notebook, and I have everything prepared, so if I get into trouble, I will copy and paste from the prepared Jupyter notebook. So this is already lecture 29 of the 8-week summer session. So we are in the middle of the 6th week. So we solve the problem of Apollonius. So in the first section, I will explain how to start formulating the equations. We have the problem of touching circles. So earlier we saw the problem, earlier in the course we saw the problem of the tangent line problem. Here we consider, given one circle, determine the location of a touching circle. Okay, given one circle, so we may as well take the unit circle. So the unit circle, there is a primitive for that. So the center is at the origin, and we have that the radius equals 1. So this is the unit circle, and I want to visualize one circle, or I want to think about circles that touch this given unit circle. So a circle is defined by a center and a radius. I have only one circle. I will show that this is a two-dimensional problem with 2 degrees of freedom. So that means that if I pick the center, that then I can still find touching circles. So this problem then still has a solution if I can pick the center of the radius. So let me illustrate that this is true. So let us pick a random center for a touching circle. So I will pick a random center, so that means in polar coordinates a random angle. So the angle is between minus pi and pi. So I have a random element, and I will take a point at distance 1/2. So my random point will be 0.5 times the cosine of the angle and 0.5 times the sine of the angle. So this is a random point. So let me first show the coordinates. And RR should be with a dot. So random element is a method of the field of 53-bit precision floating point numbers. So I also want that the pi is a numerical pi. So that's why I'm casting the symbol pi into this RR field. Okay, so I can visualize this now. So there is the plot of the point. With the point, I give the coordinates, which is the tuple. I will make a red disk. So let's make a big fat disk. And I have already the unit circle. So I will add the unit circle and display this point. So the nice thing about the randomness is that if you were to try this, and I tried this before in the recording, I will actually have a dot that is somewhere else. So one can fix the seed to make this at the same location, but in what I'm trying to show here, it would be kind of cheating. So I want to demonstrate that I can solve this problem. I will now compute the touching circle, or I will really display it just by picking this random, just for any random center. Okay, we stare at this a little bit. So what it means to be touching, it means that I can draw now all kinds of circles, so centered at this red disk. And you can see that if I want to touch, so the radius should actually be not larger than 1/2. So let me motivate this a little bit. So the distance of the red dot, of the red disk, to the circle is 1/2. So imagine a vector through that. You shoot an arrow through this red disk, then you will see that the distance from the start of the arrow to the red disk is the same as the distance from the red disk to the circle. So this is because of the 0.5. Perhaps the 0.5 might not be that good. Okay, so I hear you. So let's change this in 6.5. So I will pick another random element. So, and also plot it here. Then the distance is 1 minus 0.65. That is the radius. Okay, so let me draw this now. So the touching disk, or the touching circle, is a circle with the center is the random point and the radius is 1 minus 6.5. So I will color this circle in green. So I have my unit circle, the plot of the center, and then the touching circle. So it will be the second touching circle, so that's why I named it TC1. Oops, I changed what did I change? I changed this, but I didn't change apparently. So let me run this again. So here I have my center and here I have the circle. So I didn't auto refresh things enough. But you see that the green circle is touching the red, has centered the red disk and is touching the blue circle. So if you want to redo this again, let's try to redo this for 0.35. So I will generate another random point. So the random point now runs closer, and now I have to change also here. So now the radius is minus 1 minus 0.35, and now I will have a larger circle. So that is the first touching circle. So this is the inner touching circle. There is also an outer touching circle. When it touches here, so the distance, the shortest distance to the circle is 1 minus 0.35. The farthest one is 1 plus. So the second touching circle has a radius 1.035, and I will also color this circle in green. So now I have the plot of the given circle, the center, the red disk, and then the two touching circles. So here is the plot, and perhaps to make it a little bit more geometric, I can turn the axis off. So this is a plot, a geometrical construction. This plot shows that for one given circle, the space of all touching circles is two-dimensional. There are some special points. So putting the red dot right at the center of the blue circle will give will give in actually only one solution. So that's the blue circle itself. And you can see that this is a limiting case. So when we've seen animations, you can now make an animation for the red dot circulating or moving around at randomly, and then you draw the corresponding tangent lines. Okay, so I will not pursue this, so you're welcome to do this. So we want to go to solving systems of polynomial equations, and I will get to this to the problem of Apollonius. So what is this problem again? Given three circles, compute all circles that touch all three given circles. So I kind of motivated this problem with the picture above. So this is a two-dimensional problem. A circle is determined by three numbers. So giving one input circle fixes one of the parameters. And that was in this setup the radius. Okay, so what will my three circles be? So I will have the coordinates defined. So I will do the tuple assignment. So I have the first center, which x and y coordinates, and the first radius. So that is the unit circle. Then I have the second circle, which is centered at 2, 0 with radius 2/3, and the third circle is the smallest one, and that is centered at 1, 1. So these are the 9 numbers which define the input. So let's now plot it. So I have x, y, and r for being my variables, but I have only, well, I will have an r later on. So let me declare all variables that I need. So I will set up the equations for the circles. The fastest way to plot a circle is with the primitives, but I want to check whether we actually know the equations for the circle, and I will use the implicit plot. So this is the equation for the first circle, and let me verify the plot. So I have to define a range for x. I'm aware that there is a circle at 2, 0, so that's why the range for 3, I will fix this. And the range for y will correspondingly be fixed to, perhaps I should put a little bit more. So this is the first circle, and I'm careful because I'm suspecting typos. So the fixed size is done for me because I have a little bit of narrow window in this pre-recording. So you can see that it's actually not that good for the labeling for the ticks. So this gives a better view. Okay, so that's my first circle. So let me continue in the same code cell by writing down the equation for the second circle. and I will do the implicit plot as well. So let me try to copy and paste. And then adjust the indices. Okay, so the two circles are touching each other. So what happened is that I was using the wrong radius. Here it is. So this is my second circle. And the third circle, so I still have let me first do the plot instruction, and then I have the equation. So in a way, we have seen the implicit plot in an earlier lecture, but with the repetition here, I'm making things self-contained. So here is then the representation of the input. 3 blue circles. And if you remember the presentation from the slides, so there is one small red circle, which you would draw around in the center here. And there is one big circle. Very similar to how we formulated the equations. So how do we formulate the equations now? So the touching circle is determined by a center, and the center will be the x and the y and a radius r. So I have already the variable r for that. So what I do need is something similar to here. So I had the center, but then I had the distance 1 plus or 1 minus the radius. So I will use the same equations here. So let me copy and paste them. But now I will be using the differences. So I will call them E1, E2, E3, and I am using the difference of the radius r with the given radii of the two given circles. So my 3 equations are then formulated: E1, E2, E3. Okay, great. We are half hour in almost in this lecture, and here I have our first polynomial system. So we have 3 equations in 3 unknowns. What these equations are expressing is that the distance of the center of the touching circle for the 3 given centers is equal to the radius of the circle, of the touching circle, minus the radius of the circle of the input circle. Okay, so I hope that this is plausible. If we will solve the system, and we will also show that this is indeed a solution. We will validate the solutions. So I will solve the equations for x, y, and r, and I want that the solution dictionary is set to true. I want to the solutions represented in terms of a dictionary. So here we are. So you can see that the system is small enough so that SageMath was capable to solve this completely symbolically. So it boils down, for this instance, to the quadratic formula. So one verification that we can do is we can take the solutions and plug them into the equation, and then see whether we really have the zero. So instead of this verification, we will do a geometric validation. So there is verification and validation by plotting the circles, the two touching circles. So validation has a stronger connection. And if that is possible, then this should be done. So I have two touching circles. So the first touching circle has a center where the x-coordinate comes from the first component, and I will select the x from it. The y-center is also the first solution, and I select y from this, and the radius of the first touching circle is selected by R. So I have a tuple of three numbers, the x and the y coordinates of the center, and the radius. So here you see a little bit the benefit of asking for the solution dictionary format with this flag equal to true. Otherwise we would get equations and have to select the right hand side. So selecting from the keys of a dictionary is a little bit more convenient than selecting the right hand side of an equation. Okay, so then I have the plot of the touching circle, or perhaps let me do the equation of the touching circle. So the equation of the first touching circle is then x minus tc1 x plus. And now if I want to plot, actually the primitive is the fastest way to do this, in particular because I have already the numbers carefully selected. So there is not much that can go wrong, although so here we have, and I want to have the touching circle in red. So that was my first pair. So I have the three circles, so they're coming from here, P1, P2, P3. I was already forgotten the names. Luckily I did not reassign to P1, P2 or P3. Okay, so here you see the first touching circle, which is the small circle. And now I will repeat everything for the other solution. So I could copy and paste in the same window, but I will not do this. I will just adapt all the indices. So this is the second touching circle. and then I have the corresponding plot. So now I may have to adjust the viewing window. But let me do it first without adjusting the viewing window, and it adjusted itself automatically. Okay, good or not so good, so I can still do the viewing window a little bit better. So instead of going from 2, 3, I should have gone with Y. If I want to clean up the plot a little bit, so 1.7 looks a lot better here now. Then I get rid of the white space. Good. So this is my input now. So if I rerun this, then here we have our first solution, the first touching window, and then I have the first pair. So there are two solutions. Well, not quite yet. So this is the first pair of two solutions. First pair is always of two. So this is the first pair of solutions. There are three more pairs, and they are obtained by replacing the R minus R1 by R plus R1. So this gives for the second pair, and then etc. for the other ones. So if you want the third pair, you're going to replace R minus R1 by R plus R1. But the R minus R2 by R plus R2. So you're going to change the second equation. And then do the same for the third equation. If you do the solving, you will always get two other solutions, and you can validate them by making the plot. So that is the exercise, the second exercise, other than the animation. Okay, so I have 10 minutes left to introduce the topic of a Groupner basis. So a Groupner basis is a systematic way. So Groupner basis for a lexicographical term order will bring the equations in triangular form. So what do we have? We have the equations here. So these are the equation in x, y, and r. I have to recast the equations in a polynomial ring. So it's a polynomial ring over the rational numbers where the order is lexicographic. So that we can do this now so fast is because we have practiced this in earlier lectures. So I will have a new polynomial system, so call this Q, where I will take the expressions in the equations and cast them in this new polynomial ring. So you can see that if I ask the type of the first expression, and can do this also for the second and the third, you see that I now have a multi-polynomial from the lib singular. So singular will be used to compute the Groupner basis. So a Groupner basis is defined for an ideal. So an ideal is the space of all polynomials that you can make by making combinations from these three polynomials. So I use J, not capital I, not to confuse with the imaginary unit, which may still pop up, which will not pop up in this application. But if you solve polynomials over the complex numbers, then the I pops up. We are almost there, so I will ask now for a Groebner basis of the ideal, and that will see instantaneously come up. We see the triangular form. So the last equation is only in R. So that's because the x and the y appeared earlier and they were eliminated. So we see the triangular shape of this basis. So we can see, so that's the first, so we have three quadratic equations, 2 times 2 times 2. We might think that there are 8 solutions, but no, there are only 2 solutions. We see there are 2 solutions. So that's the important conclusion here. Now, then there is the solving. I can solve this by asking for the variety of the ideal, and I can do this symbolic numerically. So we've seen the QQ bar appearing in the symbolic numeric factorization of a polynomial, and this is also what happened here. So the last polynomial got factored, got solved with 53 bits of precision, and the numbers that we see, the coordinate values, are intervals. So we see the coordinate representations. We see that the numerical values for the coordinates are intervals. So this is a semi-numerical solving. We see floating point numbers, but we have bounds on the errors. So the diameters of the intervals actually tell us something about the accuracy. So I have still some time to illustrate this, so I can select this. So I have the variety. So the variety is the term used for solution sets in algebraic geometry. So let me select the first solution, and that's the R component. So let's see what the type of that element is. So that is indeed an algebraic number. So this first R, call it now R1. So let's see if I can see the string representation with the bracket style. Nope, I have to explicitly convert this to the real interval field. So with the real interval field, I can verify the accuracy of my result by asking for the diameter. And you see that this is very close to the machine precision. So you can also do this for the other solution. So the verification via the real interval field, asking for the diameter, showed that the accuracy of the computed solution is close to the machine precision. So this is a verification type of computation that you can ask simply by the attributes of the final results. So it's just by querying the diameter of the numbers, which are actually algebraic numbers, but they can be easily converted into the real interval field, or more in general, to the complex interval field. So a further step would be to compare this solution here with the solutions that were obtained here. So here we see the solutions in the formal notation that was obtained by solving the quadratic formula that was done here. Okay, with this lecture I'm not going over time, so I hope that this lecture was a good introduction to where polynomial systems come from and how Sage can be very useful at many levels and layers. So there is the formulation part of the equation, so we can start from a geometric input and formulate the equations and solve them, and then interpret the solutions. And if we want to go a little bit deeper into the algebraic algorithms that are applied, we can do so as well. So we can actually represent the solutions in this way in a symbolic format. So the pairs of solutions can be plotted, but here you see with Groupner Basis an algebraic representation of this problem. So for each of the pairs of solutions, one can come up with such a representation. Okay, so I will stop the recording.